Welcome to everyone who is joining us via the recording. This week we are talking about sections 3.4 and 3.5, which is some really cool and important stuff. So let's get started. Do you guys have any preference on like what section we cover the most? I was planning on doing a couple of problems from 3.4 and then moving on to 3.5, which is really kind of like the essence of everything that we've talked about so far. All right, if you guys have any questions, just yell at me or put it in the chat or something and we'll stop and talk through some stuff. All right. Let's just go ahead and start with 3.4 then, because that's kind of what we're up to right now. I am on page 242. And we're going to find some limits. So let's just go ahead and start with question 9 right off the bat. We've got the limit as x goes to infinity of 3x minus 2 over 2x plus 1. So how am I going to start to solve this problem? Like, what is my first step going to be? Well, I could just go ahead and try to solve it. But yeah, we know that because it's in the section, and we know that just like from looking at it, we've got an infinity on the top and an infinity on the bottom. So we're going to need to do something to it if we want to solve it. So we're going to compare the degrees in this. What is the highest degree that a polynomial is up to in this problem? 1, exactly. So what do I do with that information? What am I going to like do next to solve this problem? Yep, we can do that. Yep, that is definitely one way to run things. I know in the book they very explicitly said, let's divide this by 1 over, or multiply this by 1, which is in this case 1 over x over 1 over x. So that will bring us to the limit as x goes to infinity of 3x over x minus 2 over x, 2x over x minus or plus 1 over x. These x's are going to cancel. And so we're going to end up with this limit of 3 minus 2 over x over 2 plus 1 over x. So if x is going to infinity, what is my limit going to be? 3 over 2, exactly. Because as x gets really big, this is going to get really small, so this is going to go to 0. This is going to go to 0. This is just going to be 3 over 2. Precisely. All right. Let's do another one from this section. Let's go ahead and do let's do 13. This is still page 242. So it's going to be the same process. But this time we have something that looks like this. So you guys had the right exact idea. We're going to compare the degrees. So the highest degree in this scenario is going to be 2, exactly. So we're just going to kind of do that same process. Let's just divide by 1 over t squared. Or multiply by 1, which is 1 over t squared over 1 over t squared. To say that explicitly. So this is going to be t to the 1/2 divided by t squared plus t squared over t squared, and then I've got 2t over t squared minus t squared over t squared. Okay, what am I going to do with this? How am I going to simplify this? In particular, this term. This is going back to like rules of exponents, just trying to review a little bit. Basically, if we're dividing the exponents, or if we're dividing like t over, or t to the 1/2 over t squared, what we're basically going to do is like subtract them from one another. So it's going to end up being t to the -3 halves. Because if you look at this, it's also t to the 1/2 times t to the -2. And so if it were multiplying, we would like add them together. And so this would be 4/2. Does that make sense? Just exponential rules. Sweet. Okay. Then we get to this, which is t squared over t squared, which is just going to be 1. Then we're going to come along to this, which is going to be 2t divided by t squared, or just 2 over t, minus 1. And so this is, again, the limit to infinity. So what is this answer going to be? Exactly. I did write it with an attempt to kind of fool you guys. I had this written in exponential form, but the negative sign there means that this exponent is on the bottom, so it'll actually be 1 over t to the 3 halves, which basically means that this is going to 0 to 0, and we end up with -1. All right. Let's try something that's a little harder. Sorry, I'm just kind of looking through here. All right. So what are we going to do about trying to find something that's a little bit more interesting. Let's try maybe 21, which is the limit as x goes to infinity of 21 is the square root 9x squared plus x minus 3x. Okay, where am I going to start here? Any suggestions? Take the square root of underside. What do you mean by that? X plus 1. Did I write the problem down wrong? Okay. I'm not sure what you were suggesting by underside. Sorry, I'm just trying to track what you guys are suggesting. You want to take the square root of the whole thing? I'm sorry. Like, this is just like not the best venue for this. I feel like we're on the right track here. Sorry, it's been like a hot minute since I've solved all of these types of problems. So I'm trying to like combine what I know with what you guys are suggesting. So are what you're suggesting basically like example 5? Because that was how I was planning on like just working through this. So let's just go ahead and solve it. You guys are probably right. I'm just like not reading you guys correctly. And I'm sorry, that's just because I've had a really long day. Okay, so the method of solving this is just going to be, we're going to start by multiplying it. And we're going to multiply it, I guess, yeah, by the conjugate. It's just going to be x squared plus 1, or not x squared plus 1. Jesus. It has been a long day. This is x 9. This is the number 9. This is 9x squared plus x, and this is going to be minus 3 or plus 3x. Yep. Thank you guys. So we're going to multiply it by this, which again is just like multiplying it by 1. And then we're going to get this into a form that we can more readily work with. We're going to end up with 9x squared plus x. And we're just going to kind of FOIL this. So this is 9x squared plus x times the square root of 9x squared plus x minus 3x, 9x squared plus x plus 3. This is minus is on the outside of this parenthesis. And this plus is also on the outside of this. So this is first, this is inner, this is going to be like the outer, we're just foiling it. So this is plus 3x, 9x squared plus x, and then we're going to finish it off with negative 9x. And so basically these are going to cancel, and we're going to end up with 9x squared plus x minus 9x in the numerator. And then in the denominator, this is just going to be over 1. So this is going to be the square root of 9x squared plus x plus 3x, which is what we have right here. Okie dokies. So what's my next step? Factor it out. Oh, and I've got something that I can simplify right here that I didn't. So this is going to be 9x squared minus 8x. Oh, and this is 9x squared. Oops, I lost a squared in here. This is 3x times 3, negative 3x times 3x. So this is plus x, and this is minus 9x squared. And what we're going to do here is we're going to end up with 9x squared minus 9x squared, which is going to cancel out each other, and we're going to end up with x over 9x squared plus x plus 3x. Yeah. So yeah, now we've got it in a position where we can use the same like strategies as previously we've used. Okay. Sorry that was so long-winded. You guys seem to be feeling pretty good about these limits. If what I can see in the chat box is true, which I'm assuming it is. Would you guys like to move on to section 3.5? Describing functions through these limits. Reading from the graph with one for infinity. Okay, so you had trouble reading from the graph with from the graph 1 for infinity limits. Which graph is? Which figure is it that you're describing? 3.4, question number 3. Okay. All right. So we are going to take a quick look at section 3.4, question 3. And this is on page 241. We have a graph, and we're going to try to state the following. A, what is that graph's function at x is going to infinity? So what do you guys think that is? -2, yeah. And you can pretty obviously see it approaching and then basically like running along the line of -2. What about part B, which is as x is going to -infinity? Yep, it's coming right up along the 2 line, and then it's just kind of following that. So you can pretty like see it very like well visually. All right, so the limit as f of x, the limit of f of x as x approaches 1. Yep, this is going to go to infinity for both of them. And we know that f of x, or f of, here, let me write this in a different color. This is going to infinity. And f of 1, what can you tell me about this? What does this graph tell us about f of 1? F of 1 is not going to actually equal infinity. F of 1 doesn't exist. Yep. And it will be something like at f of 1, you'll end up with like some number, and then the denominator will be 0. And then you know that that doesn't exist. But as you get really close to 1, you get really close to 0, right? So it doesn't matter what's going on in the numerator. If you're at like 0.9 or f of 0.99, this is going to be approximately 0, but not equal to 0. So it's going to make this whole thing really, really big. So you're going to infinity that way. And if you're looking at f of 1.01 or whatever, it's again going to be approximately equal to 0. So it's going to be really, really small. Dividing by something that's really small yields something very large. So it's also going to infinity from that end. So the limit is equal to infinity, but once we actually get to f of 1, it equals 0. The denominator is going to be 0, and therefore it doesn't exist because we can't have that. Okay, so the same principle applies to the limit at x is equal to 3, or x is approaching 3. So what is this going to be equal to? Negative infinity. Correct. All right. And then the equations for the asymptotes. Do you guys know exactly what they're asking for here? I'm not sure precisely what they want. Are they... Oh, yeah, okay. So, got for part E, they're looking at like equations for the asymptotes, and that means like what line like the asymptote is on, like the dotted line. So that would be y is equal to, oh, it wouldn't be y is, oh yeah, for the horizontal asymptotes, y is equal to -2, y is equal to 2. So these are the horizontal ones. And if we wanted to define the vertical asymptotes, there would be a vertical asymptote at x is equal to 1, x is equal to 3. Does that answer your question? There were kind of two questions floating around in the chat. Are both of them better now? I think it was... Okay, go ahead. What determines odd or even when x is approaching negative infinity? Okay, yeah. So odd or even is talked about in the next section. And as Alexander points out in the chat, it depends on if f of negative x is equal to f of x, that's an even function, or f of negative x is equal to negative f of x, and that's an odd function. So that, I mean, like, this is like characteristic of an equation, whether or not it's approaching negative infinity. So if x is approaching, like, for instance, if you have like a line that like the slope is going to be constant, and like there are certain things about that line that are just like a characteristic of the equation. Like if we're looking at like a really simple, like y is equal to 3x plus 4, then we always know that the y-intercept is going to be 4, even if we're looking at x is equal to like 1,000,000, because Even though we're not looking at the y-intercept directly, that's like a characteristic of the function that's not going to like be changing. And so the characteristic of being even versus odd is like also like intrinsic to the function. So as x is approaching negative infinity, the function is either odd or even. It just depends on, you know, like what the function looks like. If I have an odd function, it might look something yeah, if I had an even function, it would be a parabola, for instance. And as x goes to infinity, this the function is going to approach infinity. And then as x goes to negative infinity, the function is also going to approach infinity, because as x goes further this way, this goes further up, right? So that's a good example from like an even function like perspective. A cubic function is also a good example of an odd. So I have a function that looks like that. And here I have the limit is equal to infinity, and x is going to infinity because it's just going straight up. Okay, let me take a quick look at that image that you sent me. I hope you're not sending me a virus. Problems 14 and 16. Okay. The photo is not loading, and I'm not sure why. I think it might just be my computer acting up. Give me just another second. Okay. All right. Let's just go ahead and do these problems, and I'll see if I can figure out what you mean. So I'm assuming these are from the book. Well, the degree in 14 is going to be like you're comparing this x squared to this 2x, right? And then down here, so that's in comparing like an odd versus, not odd, you're comparing like an even number to, and sorry, I'm like gesturing to this example that you sent without like actually, I don't think I'm screen sharing it. So I'll do that now. Let's see. We're going to do this. Okay. So theoretically, you guys can all see this image now. Yes. Okay. So will it let me write on this? I don't think it will. Basically, what's going on is you have this x squared, like, and this x here, and then you have this x to the fourth and this x squared here. And so this is two even functions, and this is an odd and an even. And so that would make a difference in compared, like, when like working with this type of stuff to find a limit. Does that kind of answering your question? Yeah, okay, awesome, sweet. All right, We're about halfway through this, and I really do want to get to curve sketching today because this is some really important stuff. So if we don't have any more questions about limits, then we are going to do some curve sketching. Sweet. All right. Okie dokies. All right. Let me get this. So on page 2, what is this page? It is 245. They give you kind of a checklist to go down for sketching functions. And I think it's a really good checklist just to like remember everything. Some of them seem kind of like gimmies, but others of them, excuse me, are like, you know, super important to like start approaching a problem. So let's just go ahead and start sketching some of these. Let's start with let's do number 4. We're going to have the function y is equal to x to the 4th minus 8x squared plus 8. What's our domain for this? All reals, exactly. All right, so then it like you guys can move down the checklist, but my first thing that I do is just go ahead and take the derivative. Because that's oh, sorry, something is flashing in my Zoom room and I'm not sure what it is. Okay, never mind, everything's fine. Okay, so if you guys want to take intercepts, let's do that. What's my intercepts? Yep. So that is going to be my y-intercept. Finding my x-intercept. Yep, set y equal to 0. So we've got y is, sorry, I'm going to expand this. Y is equal to 0, which is equal to x squared minus 8x, or x to the 4th, minus 8x squared plus 8. And then we're just going to kind of use algebra to solve this. I guess I didn't have to move the 8 over. So what am I looking at here? I guess I should have moved the 8 over, never mind. It was foolish of me. So what's my next step? Okay. What am I dividing by? Okay, I'm sorry. Just give me 1 second. I gotta take care of something really quick. I will be back in like a minute. Um, I'm so sorry. Okay, I'm back. I'm so sorry about that. That was drama. Okay, let's get back to this. We were finding y-intercepts, right? Or x-intercepts. We were finding x-intercepts. Give me just 1 sec to get caught up in the chat, which I see you guys were busy in, which is really awesome. Basically, my suggestion, you guys were right in saying that y is 0 at the start, so we're just like going to discount it because what we really want to find out is what x is equal to. So we aren't going to use like this kind of like algebra. I shouldn't have simplified it like that. We shouldn't have factored it. Because that kind of made it into a form that's like less usable. We're going to treat this like some people were talking about. I think it was Alexander was talking about. You guys can hear me, right? I did turn my mic on, right? Okay, sweet. Okay, so Alexander was talking about quadratics, which is exactly what we're going to do. We have this equation, and we are going to basically just, where is my eraser? We're basically just going to treat it like a quadratic equation. So let's do that. Like if x, squared is equal to x, for instance, then it puts it in a position where we can use the quadratic formula, I believe, which I'm an idiot and have to look up really quick. But let me just copy it down so that everyone has it now. The quadratic formula is going to be x is equal to negative b plus or minus square root of b squared minus 4ac over 2a. So we've got this, and so basically this is going to be wherever x is equal to one of these numbers, then y will be equal to 0. So this is like how we find our x-intercepts, right? Does that make sense? Like in this situation, we've got this quadratic like formula. We have this equation. It's equal to 0. It's in like the perfect conditions for this. So you guys were definitely on the right track in the chat. Yes, the coefficients are going to be the plugins. We just need to remember as we continue solving this that x squared is actually equal to x as we do this. So let's do this real quick. Get rid of all of this. These brackets I drew. Okay, so x is going to be equal to minus b, which is going to be negative 8, plus or minus the square root of b squared, which is going to be negative 8 squared minus 4 times a, 1, and c, 8, over 2 times a, which is 1. So just like we would do with like a quadratic form, we're just going to plug it in and figure out what this is. So this is going to be positive 8 plus or minus the square root of 64 minus 32 over 2. Yes, so this is a coefficient. A is equal to 1. B is equal to negative 8, and then C is equal to 8. And we're just, yeah. So these A, B, and C's up here are the coefficients from the formula. Okay, so we are sitting here right now. We are going to simplify this again. So this is going to be 8 plus or minus the square root of 64 minus 32, which is going to be 32 over 2. Square root of 32, can we simplify that? Yes. So this is square root of 16 is going to be 4. So this is going to be 8 plus or minus 4 root 2 over 2. And this is going to just simplify into being 8 over 2 is 4 plus or minus 2 root 2. So that is no, this is the x-intercept. And so this is, are we done here? Have we reached a point where we're done? Have we forgotten anything? Our domain is in all reals. So we're good there. There's no Yep, we're good. What we are forgetting, however, is x is not equal to x. Here, what I should have done is said this is like, I don't know, k or something random. Because this is actually equal to x squared. So, do we have the information we need right now? No, because what we want is x, not x squared. So, we have to take the square root of all of this again. So, take the square root of this, take the square root of that. X is going to be equal to plus or minus the square root of 4 plus or minus 2 square root 2. And we could go ahead and calculate exactly what all of those numbers would be. Yeah, look at that. It seems really grody. And I think we should, just really quickly, for the sake of graphing this later on. So 2 root 2 is equal to 2.828. So 4 plus is going to be, yeah, I'm gonna leave it at like 2.8 because I want to get like a little bit precise. But we're just going to go ahead and say that 4 plus this is going to be 6.8, and then we're going to have 4 minus that, which is going to be 1.2. And then we need plus or minus the square root of 6.8 and plus or minus the square root of 1.2. So our x-intercepts is x is equal to negative 1.095. X is equal to 1.095. X is equal to, and again, I'm just putting these into a calculator, negative 2.608, and x is equal to 2.608. Okay. That took a little longer than I thought I was going to, and again, sorry, I'm so sorry for the pause in between. This is what happens, I guess, when you live in the dorms. But, okay. So, you guys wanted to head down the list. So, are there any asymptotes? Oh, symmetry next. Symmetry's next. All right. How do we determine symmetry? Yep. There we go. So y is equal to negative x to the 4 minus 8 times negative x squared plus 8. What happens here? This is going to be an even, so this is just going to equal x to the 4. This is going to be negative 8, and this is just going to be the same as x squared, and that doesn't change at all, that plus 8. So they are equal. We established that f of negative x is equal to f of x, so we know that it is even. Okie dokies. Then come asymptotes. Yes, and as Alexander points out in the chat, that means that it is symmetrical around the y-axis, which will become important when we're sketching this thing out. Okay, so then come asymptotes. Do we have any asymptotes? Nope, exactly. Polynomials don't generally, like, it's just like the lines of polynomials like this don't have asymptotes like that. As x goes to infinity, they will be going to infinity or to negative infinity. In this case, because it's even, we know that they're both going the same direction. Okay. Then intervals of increasing and decreasing. How are we going to find this? Mm-hmm. All right. So here is my first derivative. What do I do next? Yes, factor, and then we're going to find it as equal to 0. So we're going to say this is equal to 0 because we're trying to find critical points. We're going to factor out 4x, so we end up with x squared minus 4. And so we know that x is equal to 0 or x squared minus 4 is equal to 0. So this is x squared is equal to positive 4 square root of x. X is equal to plus or minus 2. All right. So, and I see in the chat we have a positive 4 mentioned. That would be the case if this was an x squared here, but since we are pulling from this, yep, exactly. This x cubed. Okay. So then the best way that I found to do this is to just make this line. Say that we have -2, 0, and positive 2. So basically, choose a point like below -2. Could be like -10. That's kind of how I do it. I just pick something that's easy to calculate. And we can just kind of plug it in here. And I always do use this factored form because it makes things easy. So if y prime is equal to 4x, x squared minus 4, and x is equal to -10, then y prime is going to be, this is negative. I'm going to move this just a little bit. This is going to be negative times 10, -10 squared is going to be positive, minus 4 is going to be positive. So when x is equal to -10, it'll be a negative times a positive, and so it's going to be negative. At -1, this is going to be a negative function. This is going to be 1 squared minus 4, which will also be negative, so we have a positive here. At x is equal to 1, this will be positive, this will be negative, because this will be 1 minus 4, so negative. And then finally, if we have like a 10 here, this will be positive, and this will also be positive. So this is basically what we were doing last week, making this number line, figuring out increasing and decreasing, all of that jazz. Okay. Sweet. So we've also established like what our critical points are going to be. And with these critical points, we can move on to number 6, local maxima and minima. Yep, we could do the second derivative to find concave up or down, but you can also just kind of do it using the first derivative to find local maxes and mins, because if you're moving from a point where your first derivative is negative to a point where it's positive, you know that you're going to have a min here. If it's going from positive to negative, then at the critical point 0, you're going to have a max. And then again, if you're moving from negative to positive, you're going to have a min. So I just kind of go through. You're right, I did just erase the first derivative, which was foolish of me. But inflection points, we are going to find out using the second derivative. So yeah, we can do that next. You're right, I did just find what x is equal to find the direct min and max. You're correct. So I'm going to quick write out this first derivative again because I accidentally erased it. And then we'll do that so that we have exact points. So we know when we have mins and maxes. We can go ahead and say that y, move this down a little bit, y is equal to, in this case, x is going to be -2. We'll just start moving left to right. This is -2 to the 4 minus 8x, or not x, -2 squared plus 8. And so 2 to the 4 is going to be, what, 16? So this is going to be 16, and it's going to be positive. Minus 8 times -2 squared is going to be 4 plus 8. So this is going to be 16 minus 32 plus 8, -16 plus 8, and -8. So we have a min at -2, x is equal to -2, y is equal to -8. And we have another one, because we know, based on our even functionality, that f of -x is equal to f of x, we can just go ahead and assume that because this would be -x and this would be x, they're like interchangeable and they have the same y value because they're symmetrical. Okay, then we just need to figure out what it is at 0, which is pretty easy. We plug in 0 for all of the x's in the original function, and we end up with at x is equal to 0, y is equal to 8, which is ironically also our y-intercept. So we did that already. Sweet. Okay. Has everybody followed me up to this point? We just finished with step like 6 or whatever. I think in the book it's done by letters, but we just finished up with finding our critical points. Okay. All right. Or maxes and mins, excuse me. So the next step in is we are going to need to take the second derivative, y prime there. So y double prime is going to be equal to 12x squared minus 16. Somehow I erased an 8. I don't know how that happened. Okay. Yep. This is a little bit easier to work with. So what we can do is just say this is going to be equal to 0. We can factor out this 4, so it'll be x squared minus, or excuse me, 3x squared. This is going to be for both concavity and inflection points, because we need to figure out the second derivative for both of those. the inflection points will allow us to determine concavity. So we're going to first find inflection points and then use them to determine concavity. Okay. So I just went ahead and factored out that 4. Because 4 can't equal 0, the only option for this is going to be where 3x squared minus 4 is equal to 0. So that's where 3x squared is equal to 4. I'm going to divide both sides by 3. So x squared is equal to 4 over 3. And then we take a square root. So I'm going to go ahead and draw this line. We have negative square root 4 over 3. And then we have positive square root 4 over 3. In between them we have 0, and on either side we have, I don't know, like 10 and negative 10. Okay. So then we're going to pick numbers that are on either side or in between of these points. These of which, by the way, are our inflection points. Plus or minus square root of 4 over 3. All right. So, let's go ahead and real quick just put these into the original equation to get out what these inflection points are. Points of inflection, that's going to be y is equal to, we can just do this once, we know, because it's plus or minus 4 over 3 to the 4th minus 8 times 4 over 3, square root of 4 over 3, square root of 4 over 3 squared plus 8. This is going to be 4 over 3 squared minus 8 times 4 over 3 plus 8. Then this is going to be 16 over 9 minus 8 times 4, 32 over 3 plus 8. And I'm just going to put these all in terms of over 9. So this is going to be 72 over 9. And this is going to turn into this will be 88 over 9 minus 96. Minus 96. Oh, yeah, sweet. 96 over 9. So that is going to be what? Negative, that's 8, and yeah, negative. It will be negative, I believe, because this is 88 over 9 minus 96 over 9. So this is 88 minus 96, which is negative 8 over 9. So it'll just be negative 8 over 9. Yeah, I added that, right? 16. I added these to get this. Here, I'll just write it all in terms of 9 over 9. Oh, okay, sweet. Okay. Sorry, I just did that because that was what I already had in terms of 9, and I didn't. Okay, so it's negative 8 over 9. Our points of inflection are, we have 2 of them. They are square root 4 over 3, comma, negative 8 over 9, and negative square root 4 over 3, comma, negative 8 over 9. So these are our points of inflection. Sweet. Then we can go ahead and put this into this equation up here. this is our second derivative. So we're going back to the number line right now. I know we've been doing a lot of jumping around. Here we have -10, which is just like a point to the left on the number line of our point of inflection. And this is going to be 4 times -10 squared times 3 minus 4. So this is going to be positive times a positive. So this is going to be positive. At 0, this is going to be this is going to be positive, and this is going to be 0 minus 4, which is negative. So we've got negative right there. And then here we have a positive, and again, this is going to be 100 times 3 minus 4, positive. So what does it mean to have a positive interval in this sort of area? Concave up. Yep. So this is concave up, concave down, and concave up again. Okie dokies. Sweet. So I think at this point we can just go ahead and start graphing this monster. I am going to see if I can move this as a group. Maybe I can, maybe I can't. I'm not sure. I can. I'm gonna move this over here, just so that I have a little bit more room for drawing this. Okay. So I'm gonna start. I know my domain's in all real numbers. My y-intercept is going to be equal to 8. So I'm just gonna call this 8. So in terms of, it's going to be 4, 8, 12, 16, and so on. I'll just do the same kind of scale on this other end. Okay. Go ahead and start by graphing these intercepts because we know that they're big and important. I'm going to establish a quick scale on this side. We're going to have, this will be -1. I'm going to stretch it out a little bit more over here so that we can get a better visual on basically like how these X-intercepts are going to interact with one another. So 1, 2, 3, 4. Okay, so here are my X-intercepts. I've got one at like 1.1, so just above 1. And then I've got another one just below -1. So these two are graphed. Now I'm going to graph this. This is -2.6. Here's about -2.5, -2.6. We'll call it right about here. And then 2.6 right about here. So I've graphed my intercepts. My y-intercept here at 8, my x-intercepts here. Then the next thing that I do in terms of graphing is I kind of determine where those mins and maxes are. I know I have one here. I also am going to have one here at 2 is equal to -8. X is equal to 2, -8, and x is equal to -2, -8. Sweet. Can you guys kind of see how this is like shaping up? Like I could, yeah, awesome. I could kind of sketch a line between these right now, and it would be kind of a W shape, and that is kind of what we're going for because we do have a function that is number 1 even and number 2 to the 4th power. So that's kind of what these graphs look like. All right. So I am going to, yep, an even symmetry on the y-axis. So we are going to kind of go ahead and just sketch a little bit of this out. And see how they so we kind of have this part sketched, and then we know from here on out, from the point +2, and as x gets larger and goes on to infinity, we know that this is just going to remain positive. We're going to be increasing this entire way. The slope will be positive. So we're going to increase. And we know that if x is coming from -infinity towards -2, it's going to be decreasing the entire way. So as we approach from -infinity and reach -2, it's going to be a downward slope. So we've kind of established a little bit of what this function is going to look like. Okie dokies. So at this point, instead of saying, all right, so, you know, like, what's going on with this? Like, how exactly can I incorporate these inflection points? And I am going to quick take the square root of 4 divided by 3. So the square root of 4 divided by 3, in case anyone was wondering, is equal to 1.155. Okay. So basically what I do is just check to make sure things are the case. So I know that I have a minima here. I've got my mins and maxes in the right place. Where are things concave up and where are things concave down? All right. Well, I have concave up in this region as I'm approaching -1.15, which is about right here-ish. So that makes sense that I have CC up in this area. And then from here to about here-ish, I have CC down. And then from here to here, I also have concave up because that's kind of what is established right here. So these pink are going to actually be my, I'm going to change this from pink to blue for the sake of clarity. These are going to be my inflection points. And then -8. So this is going to actually be, because, all right, let me erase some of this so that I more clearly can establish what's going on. Because we determined our inflection points are going to be at this point right here. So this is going to be and then down here is going to be .16. So it's a very slight difference in the x value, right? But a larger difference in the y value. So I'm just going to make sure that that is a part of my curve, that I make sure that I get those points in the correct location. But we have established that my concavity is looking pretty good in terms of what this graph actually does look like. So I'm going to go ahead and I'm going to sketch this thing in black because I think I know what it looks like. So I'm going to be going from that end. Actually, can I adjust? Yeah. that's gross. Never mind. Be coming from this end. I'll be coming down. I'll meet my my x-axis. I'll go down. I'll meet that minima point as I'm coming back up. I hit my point of inflection, and then I hit my x-axis again. Or not x-axis. I hit the x-axis. I hit my x-intercept. Up to my y-intercept, and down again to my x-intercepts. So I've got this nice concave down region here, down and back up. And then again, my function will be increasing towards infinity. So that is what it looks like. Okay. That is how everything got put together. Sweet. Unfortunately, I don't have time to do another one. I actually have another GSG session starting in like 10 minutes. So this is all I can do for now. Do you guys have any questions on what we just did? Okay, thank you guys for being so patient this time around. I'm sorry that we took that little break in the middle, but I hope you guys did learn something about limits and sketching these functions. And that all of this information is like necessary for making sure that your function is correct. I will tell you that there have been times where I went ahead and like only did the first derivative and was like, it's going to be fine. I can just like kind of estimate where everything else is because I was on an exam and I thought, don't have time to figure out points of inflection and concavity and all that stuff, and you get the problem wrong because there are just things that you didn't check. So you do want to try as like time giving, like if you have enough time to do the whole problem, just to make sure that you're definitely on the right track. So yeah. All right. I hope you guys have a great evening. Yep. I will see you guys next week. It will probably be at our regular time of 7 p.m., but there is a chance that we will need to reschedule for earlier in the afternoon again. And honestly, I've been getting better turnout in the early afternoon, so I'm wondering if that's what we should continue doing, just for the heck of it, because more people seem to be showing up. So we'll see if that's how we go. Anyway, thank you guys so much for coming, and I hope you have a great evening / afternoon.